Hello and good morning, afternoon, or night, depending on where you might be around the world. On behalf of EMD International, I would like to welcome you all to today's webinar on the site compliance module in WindPRO. Today's presenter will be Lasse Svenningsson from EMD International, who is the main person responsible for the development of the site compliance module. The presentation should take probably around 30 minutes, and there will be a short question session at the end, followed by a very brief survey. We ask that you please submit your questions in writing in the questions section to the bottom of your GoTo interface. You can expand the questions section by clicking on the plus symbol just to the left of the word questions, then type your text in the window that appears there below it. Questions will be answered during the Q&A session at the end, and questions will not be accepted once the Q&A session has begun. So please submit your questions during the presentation. If we do not get to your questions, don't worry. We will be sending out a link to the Q&A summary as well as a recording of this webinar to all attendees within the next few days. So now I give you to Lasse Svenningsson, who will be taking you on a guided tour of the site compliance module in WindPRO.
Thank you, Nathan, and welcome everybody. Welcome to this guided tour of site compliance. So as you see now, we're looking at WindPRO in the maps and objects, and during this guided tour of site compliance, within the next half hour, I'm going to show you how to make a suitability assessment with site compliance. That is, I'm going to show you how to evaluate if a particular wind turbine design class is suitable for a site. And the site I'm going to use is the site that you see right here. It's a site in northern Poland. It has two measurement masts on site, and it has a wind turbine layout here with two groups of wind turbines. And we also have some site data objects. So let's assume that we have already done a long-term correction. So we have done a long-term corrected wind statistics for either of the two masts using the MCP, and they are defined here in these two blue site data objects. So let's go to the calculation window, and let's see here. We have already these calculations. So you see the MCP calculations, and there's a park calculation using these long-term corrected wind statistics. What we also see here on the right is that I have a license, a valid license for WASP, that's the green dot down here in the lower right, and also a valid license for WASP Engineering. And to start the site compliance calculation, we need to go to the group here in modules called loads, and we can click on the site compliance module. So let's give this calculation a name. And let's start out by looking here at the bottom of this main page, because here we see the TÜV Süd logo and a text saying that the site compliance module has been certified by TÜV Süd to comply with the IEC 61400-1 edition 3 standard. And this means that the different calculation options we provide to you in the site compliance module have been evaluated by TÜV Süd, and they found it to be in compliance with the requirements of the IEC standard. If we move up a little here, we can see that we can choose the wind turbine design class to assess. It is possible to define it individually in the different wind turbine objects. However, in most cases, all wind turbines in a layout will need to be of the same design class. Although not a requirement, it is the typical situation. And in that case, we can choose here to overrule and simply define the design class we want to assess here in the module. And let's assume that we want to assess a class 3B wind turbine. It's also possible to assess even a generic class, the class so-called class S. In that case, we would need to insert the generic values down here in the table specifying the IEC parameters. So for this class 3B, the design criteria is an extreme wind speed of 37.5 meters per second, a mean wind speed of 7.5 meters per second, and a reference turbulence intensity of 14%. Let's go a little bit up here and have a look at the three main modes of use for site compliance, which are specified here in the upper part of the main tab. The first mode is referred to as no mast data. That would be the situation where you are calculating for a site where there are no on-site measurements. You just have your wind statistics and some reference turbines to calibrate it. The second mode here would be where you have only mast measurements and you don't have a license to either WASP or WASP Engineering. That could be an offshore site or a very preliminary assessment where you want simply to base your assessment just on the measurements. And the upper one here, the last mode, is the most typical one, and that's the one I'll select, where we have both on-site measurements and we have access and license to the flow models. And as I select that, you see I get access to the flow models down here, and we can select which flow models to include. And as I select WASP Engineering and WASP, you see we get a tab up here. It's important to emphasize here that it is not a requirement to have a license for WASP Engineering to do a full suitability assessment inside compliance. So this would be a fully viable option. However, if you have a license for WASP Engineering 3, you will have additional calculation options which for some checks will allow you to make a more accurate calculation. So in this case I have a license for both. I'll select both, and we note here that there's an additional setting for WASP where I have the option of choosing to use the mast data directly in WASP or to use the long-term corrected wind statistics. And in this case I have long-term corrected wind statistics, so I want to use that option. And we're ready now to proceed to the next tab. And let me just mention here that the first tabs here up until the link tab is the setup of the site compliance with the data and the flow modeling, and the actual IEC calculations here are all performed on the final tab called calculations. So on the second tab here we select the site masts, and we have two site masts called Casino 1 and Casino 2. So we select the main height, which is the height used for the turbulence data and the extreme wind samples. And we have to also mark the heights to be included in the wind shear calculations. And here on the right we note some information about the measurements, the sample rate, the duration from the first to the last enabled sample, and the recovery rate. And if these deviate from recommended values, you would have a red warning here. It will not block your calculation, but it's an indication that you should perhaps look into your data and maybe disable or handle your data. Let's add the second mast in the same way. And we've now added our two site masts, and we can proceed to selecting the wind turbines. And this is the well-known dialog box also from the Park module. And we can select, you see we have 15 new wind turbines, and at the bottom here we have the option of selecting the ID to be used for each turbine, either the full description or a user label. In this case I have a user label which is more convenient to use. And we can proceed to the next tab, which is where we decide which mast to use for which wind turbine position. The default is to use the nearest. However, we can shift to manual mode where I can decide that link. And that could be based on other criteria, could be forestry, exposure to forestry, or general exposure in the terrain. Let's stick to the nearest in this case. And now we're ready to look at the WASP calculation. And so this tab actually defines an interface to the WASP flow model. And for the option that we chose to base it on the long-term corrected wind statistics, we simply have to choose the site data object that holds that long-term corrected wind statistic for each of the two masts. And once done, you can see that we can start the calculation. And while that calculates, we note here that the option here is activated that we will automatically calculate also the wind climate at the bottom and the top of the rotor to be able to estimate the shear across the full rotor. And now we see the WASP calculation has completed, and we see a green tick up here on the WASP tab. So we can proceed to the WASP Engineering calculation, and this tab is actually now the graphical user interface for the flow model in WASP Engineering, also called LeanCom. And we've made some simplifications to make it easy to use. First choice is to define the terrain and roughness. That's done by selecting a site data object. In this case, they all refer to the same terrain and roughness data, so it doesn't matter which I choose. The two extra choices here is to define a buffer that defines the rectangular calculation domain. The default is 5 kilometers in a buffer added to the outermost wind turbine or mast position in the domain, and also a grid resolution which defaults to 50 meters. Based on those two, we get the number of grid points for our calculation domain, and which is subject to some recommendations specified down here. So let's, with those defaults, start the WASP Engineering calculation. This takes a little while. It takes around 4 minutes. So it's a more heavy calculation than the WASP calculation, but it's also done for an entire domain. So while that's running, let's talk a little about the differences and advantages from the two flow models, WASP and WASP Engineering. So the WASP model is basically a single point calculation. So it does a calculation for each wind turbine position, and it focuses on predicting the annual mean conditions. That is the Weibull distribution for each sector. And in doing that, it has a stability correction that has a strong influence on the vertical profiles. So the WASP profile is at least per default, strongly influenced by stability. On the other hand, we have WASP Engineering, which first of all does its flow calculation for the entire domain at once. That's what we specified here, set up that rectangular domain. And it is a purely neutral model, which means that it doesn't have any stability correction. And this makes WASP Engineering particularly suitable for calculating speed-up factors at extreme wind speeds, where we tend to have neutral conditions. WASP Engineering also predicts flow parameters like the vertical flow inclination and the wind shear. It also calculates turbulence. However, that's actually not done on the grid, but in a post-calculation for each turbine position. And this is actually what takes most of the time that we're waiting on right now. So the turbulence calculation is the most heavy part of the WASP engineering calculation. And so one thing here is that the turbulence calculation in WASP engineering is actually quite advanced. It calculates the 3 components of turbulence, which are useful, as we will see later on, in particular for complex sites where the IEC standard has certain requirements relating to the turbulence component. And so relating to the WASP engineering interface, again, what is required to be able to call WASP engineering here is a license that is activated for WASP Engineering 3, and obviously also WASP Engineering needs to be installed on your computer. But again, it's important to stress that you can do a full suitability assessment with site compliance without the WASP Engineering calculation. It will just add some additional calculation options. And we just need the final step here, and in a short while we see that now the WASP engineering calculation has completed successfully, and we have a green tick mark here for the WASP engineering calculation. So we are now ready to start the actual IEC calculations, and let's just take a little overview here of this calculation tab. At the top we're seeing that we're calculating according to the IEC edition 3 standard, and we're assessing whether a class 3B wind turbine will be suitable for this site and layout. And then we have our result legend, but let's get back to that once we have our first result. Down here at the actual checks, they are split in two groups called the main checks, which are the, you could say, the key checks in the IEC standard for assessing a site. And we have some additional checks where there are actually several in the standard, but we have selected the 3 which are most likely to be critical, but also makes most sense to include in a site estimation. So to start these calculations, we will simply click include here to add the main checks. And what we note here is that there is an interdependence. It is not possible to start the effective turbulence calculation, and it says missing terrain check. And this indicates that before we can do the turbulence calculation, we need to do the terrain complexity check. And that's because the IEC standard specifies certain correction factors that needs to be introduced in the turbulence calculation if a site or turbine position turns out to be complex. So we're ready now to start the first check, which is the terrain complexity. It's the simplest check, so it's a good starting point. So I access it by clicking edit, and we see here the setup, which is very simple for this check because there's only one option, namely using the digital elevation model specified in the WindPRO project. And then there's a grid resolution which per default here is automatically set to fulfill the IEC requirements. And to perform the calculation, we click calculate down here at the lower right, and we immediately see the results in terms of graphics here on the tab called graphics, and there's also a tab with the results in a table format. So let's just go through this graph. So it shows us the terrain complexity index for each of the wind turbines. And in this case, we see that it's 0, which means that the wind turbine positions are simple. There is no terrain complexity here. And there's also a rather flat site. We can also look at that in the table format, where we can see the terrain complexity index for each turbine. And we can expand and actually see some of the sub-calculation results as part of the requirements, the IEC requirements for this terrain complexity check. So let's have a look here at the right part, this right pane, where we have a button called Add New. So let's add a new calculation here where we can make another setup. Again, it's pretty trivial in this case, but let's assume we would like to test another grid resolution just to show you how easy this is. Let's call this 50 meters and press calculate. So what we see here is that now we have 2 calculations here in the calculation list, and it's completed now, and we can toggle between them to compare the results. And we see in this case that they are fully consistent, so it doesn't matter which calculation here that we would use, which resolution. However, before we click OK and close down the terrain complexity check, we have to decide which of these to use in our final assessment. And that's the one marked here by this small black dot. In this case, it doesn't matter, so let's stick to the default setup. And now we see we have a green flag here, and let's go to result legend and see what it means. So a green flag means that no wind turbine exceeds the IEC limits. A yellow would mean caution, and that at least one wind turbine exceeds the IEC limits, but that the exceedance is not considered to be critical, so it's a minor exceedance. Whereas the red is a critical warning, which will indicate that at least one wind turbine position exceeds the IEC limits and that the exceedance is considered to be potentially critical. So let's proceed to some of the simpler calculations here. Let's take air density. And here we see we have a few options. First option is to base it on temperature measurements at one of the site masts which hold temperature measurements. Let's try that default. And again, we see the results. We see the air density for each wind turbine position, and we see that it slightly exceeds the IEC limit here indicated by the thin blue line. again, we can see the results table, and we can even see the base data, which are the data that went into the calculation. Let's add another calculation and try the other option here, which is using data from the historical climate database, which you might know from the PARC module in air density correction. Let's try calculate here and compare the results for these two calculations. And we see that they are very consistent. And again, we have to make a choice, but since they're consistent, let's rely on the mast measurements. However, it would not make a significant difference in this case if we had used the other option. This time we got a caution here. It was a small exceedance of the IC limit, which is not considered to be critical. Let's proceed to the wind shear check. Here we have several options, and one thing to note is that they have been ordered in a way, and we have assigned a quality. This is not related to the IC standard as such. This is a quality stamp that we have defined to be able to provide a default option for you that, given the data that you have set up and your flow model results, that is expected to be give you the best results. So the highest quality here, the uppermost calculation available, will always be the default in your calculation. In this case, this is using the relative variation of shear predicted by WASP Engineering at the masts and wind turbine positions combined with the shear at the masts. So let's try this default option. And again, we see the results in a graphical way here, that all wind turbines are just within the IC limits of a wind shear of 0.2. So it's a green flag. And we can also have a look at that in the table. So let's proceed to the next check, which is flow inclination. It's also a rather simple check. We have two options, either using vertical flow inclination from WASP Engineering or from the terrain complexity check, which is something that is mentioned in the IC standard that you are allowed to do. Let's use the default option in this case, and we see that it's a flat side. We have no significant variation in the inflow angle, and everything is within the IC limits here of ±8 degrees. So again, it was a green flag for flow inclination. So let's do the wind distribution check. In this case, we have three options. We can base it on the WASP prediction, in this case using the long-term corrected wind statistics, or using the mast directly, including the sector-wise here to extrapolate from measuring height to hub height, or simply use the mast data directly, assuming that it is representative for all turbines. So in this case, it's obvious that the WASP calculation using the long-term corrected wind statistics will be most appropriate. And again, we see the results. And this time, it's a little different because we see the result for each wind turbine, and we see the distribution, the frequency distribution of wind speeds, and we see a highlight of the interval specified by the IC standard, which is the vertical blue lines. You see the thin blue curve here, which is the IC requirement, and the red curve here, which is the wind turbine distribution. And then we see the exceedance here, which is highlighted in light red. And in this case, the exceedance is considered to be critical. So let's go to the table where we see the same thing for the appropriate wind speeds. Let's close it. So now we got a critical for the wind distribution check. Now we have the two most important and most, you could say, complex checks back. So let's start out with the effective turbulence check. and here we have quite a bit of calculation options, but they are grouped in several boxes here. And the first box represents how should the ambient turbulence measurements be handled, because there will be outliers and there will be wind speeds and directions where we don't have sufficient data. So this needs to be treated, and there are some settings here which have proven to be quite robust and work really well. But you can adjust them and test them for your site. The second box here defines how the measured turbulence values will be scaled to become representative for each turbine position. The third box relates to the turbulence structure correction. That is the outcome of this terrain complexity check that the IC requires, that if a site is complex, you need to apply a correction factor, which can be based on different options here. Fourth box is the setup of the actual effective turbulence calculation, also called the function model. And last, we have a simple sector management here. So let's click calculate for this default setup. And again, we see the results here for each wind turbine. Right now, it's shown as the standard deviation of wind speed. Let's change to turbulence intensity, because this is probably more familiar to most of you. And so we see here the required check range from the IC standard. We see the IC requirement as the blue curve, and we see the calculated effective turbulence for this turbine as the full red curve. But the red dash curved here is the effective turbulence using only the ambient turbulence, not the wake added. So the difference between those two red curves indicates the effect of the layout here, which is actually what exactly brings this one to slightly exceed the IC requirements. However, this exceedance is not considered to be critical if you focus here on the upper red corner. We can also have a look at that in the table format, and we can go and have a look at the actual fits of the turbulence measurements. And here I'd recommend you to go to standard deviation, because this is the most appropriate view. So let's just toggle between the different sectors. Here you can see the turbulence measurements for the first mast, and let's go to sectors here. You can see how outliers are selected based on, or excluded based on, some objective criteria, as the number of samples required to include a particular bin. At the end here we have an additional results tab with the graphics, which is quite nice to get a better understanding on the effective turbulence model. So for each wind turbine, we can see the turbulence rows with the different contributions. We can change the wind speed down on the scroll bar down here. Right now it only shows the ambient turbulence at 50 meters per second. We could add the wake turbulence and the total turbulence, which is the combination of the ambient and the wake turbulence, and then the effective turbulence, which is the integral of the total turbulence over all directions. And that you can toggle through different wind turbines here to see how these different contributions add up. So that was a minor exceedance, but not a critical exceedance for the effective turbulence check. So let's do the last main check, the extreme wind check. Again, we have multiple calculation options, but they are grouped. First group here is the statistical model, where we select how should the extreme wind speeds be extracted and which statistical model should be used. So the default here is the peak over thresholds model, also called the method of independent storms, or MIS. The second box here is how should the extreme wind samples be scaled from the mast position to better represent each wind turbine position. And at the bottom here, at the third box, we have some additional model settings. So let's press calculate with this default setup. And we immediately see that actually all wind turbines exceed the IEC requirement here for extreme winds. We can view that in the table format. We get the red warning, and we can even evaluate the Gumbel fit for each wind turbine. And we also get a nice view of the time series and the extracted extreme samples for each of the two masts. So let's click OK, and now we have the complete assessment here, indicating that we have a violation which is potentially critical for both the wind distribution and the extreme wind, which indicates that a wind class 3 is probably not a good choice for this site. We could consult the manufacturer. It could be that there is some additional load reserve in a particular wind turbine model. However, let's instead make the assessment: would a class 2B, so what if we increase the wind speed class by 1? Would that be suitable instead? So we go back to the main tab and we change the class to a class 2B. And we go back and we see now the results have been cleared. But by pressing recalculate here, all the calculations that we set up will be recalculated. And we see now, going to a class 2B, our potentially critical exceedances with the extreme wind and the wind distribution have been resolved. And it appears that a class 2B would be a good choice for this site. So let's proceed to the other checks, which are very fast. Let's include those. And let's start with the seismic hazard check. It's very fast. It's based on a global seismic hazard map compiled by the UN. And we press calculate, and we get the seismic hazard, or the peak ground acceleration in an area around the site. And we can see the peak ground acceleration of 0.3, which is a very low seismic hazard. The lightning rate check is similar. It's based on a database provided by NASA. And we get the lightning rate in terms of the expected number of strikes per year per square kilometer, which is 1.5 strikes per year per square kilometer for this site. And finally, we can do the check temperature range, where we can assess whether we need a special temperature version of the wind turbine. We need a temperature time series, and in this case we have that for one of the masts. There is a decision here on what kind of fit to make to those data, either fit a full Gaussian or focus on the two ends of the distribution. So let's take that one, and then we can define the design limits. So let's check the standard temperature limits here. We can change that to calculate for a high or low temperature version. So these are the results. So in the upper plot here, we see the cumulative distribution function of temperatures, and we see the normal range and the extreme range specified for the standard temperature class in the IC standard. So that's also called the operational range, where the turbine operates, and the survival range, where the turbine is able to survive. On the lower plots here, we zoom in on the lower and the upper tail, and we change the y-axis have been changed to show the number of hours below the particular temperature. So for this example here, we can expect to have 10 hours a year below minus 10 degrees Celsius. And we see that this is green, and we can go to the result table here, where we see the total number of hours outside the normal range, which is expected to be 8.6, and 0 hours expected outside the extreme range for each year. So with that, we have made a complete assessment in the site compliance module, and we have found that a class 2B wind turbine would be suitable for this site and layout. So let's click OK here, and let's just have a look here. We see that we have a complete list of report pages here with an overview, park results, wind turbine results, and then a sub-report for each of the checks. Let's just have a brief view at the main report. Here we see the main calculation assumptions, and we see an overview of the results of the checks. We will put out a PDF sample of this report together with the recorded webinar so that you can have a look at the different pages here. So now let's leave WindPRO, and I'll give you a little teaser of what which new things you can expect in WindPRO 3.0, which is due to be released in 2014. So we have two groups of new improvements. One is related to introduction of WASP CFD results in site compliance, and the other is related to the development of load calculations. And we're working on these things right now. And just to give you some more details, so the introduction of WASP CFD calculations will allow some advanced speed-up calculation options and also advanced turbulence scaling. And we'll have more detail in also accounting for the turning of wind turbine wakes. So regarding the the load calculations, so what we are introducing is what could be called a super fast fatigue load assessment based on generic load response models. And this will allow you to assess the critical components and the expected component lifetime. And where it really will add some value is the case where you have one IC check which is considerably exceeded, and you have, so that's red, and you have all the other checks are green with a significant buffer. Will that buffer balance the exceedance? Well, the answer is given by the load assessment. And the last point here is that turbine manufacturers will be able to introduce their own models in the software. So with that, I'll give the word back to you, Nathan.
Thank you very much, Lasse. Very good presentation. Okay, and that now concludes the presentation portion of the program. All of your questions have been forwarded to Lasse. We'll give him a second to look them over, and we'll begin the Q&A session shortly. In the meantime, I would like to point out the ways in which you can contact us for further information about the site compliance module or to place an order for it. You should see on your screen here now a series of ways in which you can contact us. First, we will be having a site compliance one-day training course coming up in March. That will be here in our home office in Aalborg, Denmark. So please contact us if you would like to sign up and attend that class. The site compliance manual is also available on our knowledge base site along with all our other manuals, best practices, and similar information. You can access that at any time. And the recording for this webinar and the Q&A will appear at the very beginning of next week also on the knowledge base site, but we will send you a link to that within the next day or so. You can always call us there at the number on your screen during the standard business hours and speak to somebody, or you can email sales@emd.dk. If you have questions of a more technical nature or you're having issues with your site compliance module that you're already using, you can contact us at support@emd.dk. So I think now I will hand the microphone back over to Lasse to answer some questions.
Thank you, Nathan, and thank you all for the very appropriate questions here. So I think we have time for a handful of questions. Let me start here with the first question. By the way, we will answer all questions, but most of them will be in writing that you can access afterwards. But let's see here. So a question here is WASP version 11 necessary to run the site compliance module? And the answer is no. You can do the assessment without any WASP calculation based directly on the mast, but of course that's assuming that mast is representative for the wind turbines. But in terms of WASP version, you can also use, if you have a license to say WASP 10.1, that can also be used in site compliance, and also the older one called, I think WASP 6 to 9. So that's WASP 11 is not a requirement. There's another question here relating to, is there a maximum number of grid points that I would recommend for the WASP engineering calculation? Well, as I indicated in the guided tour, there is a box just below that states some numbers, and it's because that when you extend, the way that the WASP engineering works is that if you extend the domain, it might not increase your calculation time, but it will at certain thresholds of the number of grid points. And so it's important to be aware of that, so that you can choose your number of grid points so that you are just below one of those transitions, so that you get maximum number of grid points for the calculation time. But I would say that the upper limit is mainly determined by your computer power, what we have chosen, the buffer of 5 kilometers and the grid resolution of 50 meters is typically a good compromise. What as I also indicated in the guided tour, what really costs in terms of time is the turbulence calculation. And it is an option if you go into the advanced settings for WASP Engineering to turn that off. But of course, then you will not have that as part of your options. So I would say that usually if you are below around, I've not seen crashes if I stick below, say, the 640 limit, but it depends. With the recent versions of WASP Engineering 3, my impression is that it has become quite stable. So let's go a little further down here. So another very good question here is, how do you determine if a turbine is yellow or red? What is the threshold value for that? And it is not a secret, and of course it's something that that is based on experience and our insight from load calculation. If you go to the site compliance manual, then at the end of the manual there's an appendix where these thresholds are stated. So that would be the place to look for that. But they are based on experience from a lot of load calculations. There's a question here: how is the displacement height included in the calculations for forested sites? And it is used in the ordinary way, you could say, just in the same way as it will be used in a WASP calculation. So if you have a displacement height on the mast, that will be taken into account where appropriate. That is in the flow modeling. And if they are set on the wind turbine position, wind turbine objects, it'll also be included. There's a question here that relates to that in my calculation I had some green checks and I had some yellow checks. And the question is saying that I changed the IC class to a class 2B, but I still had a yellow flag for the effective turbulence calculation. And how can I conclude that the turbine is that the class 2B turbine is a good choice since the turbulence is exceeded? And well, it's also an approximation, you could say, but there is the decision on when there is a transition from yellow to red for the effective turbulence is based on an approximation where the trade-off, because there was an exceedance for some wind speeds for the effective turbulence check, but there was a buffer at other wind speeds, and then there's a calculation going on that weights these two against each other, and generally the exceedances at higher wind speeds are more severe, and there we had actually significant buffer, or at least some buffer, and so the calculation that's going on inside site compliance does this weighting and compares. But of course, you're right. Eventually, a turbine manufacturer will for their particular wind turbine will make an assessment that will also include things like some load reserve. So I think that's it for the questions that we'll be able to include here in the webinar. And with that, I'll thank you all for those very nice questions. I'll look into those later here. And with that, I'll give the word back to you, Nathan.
Thank you very much, Lasse. And that's time for today's webinar on WindPRO Site Compliance module. When the webinar ends, a close button will pop up in your go-to interface. Please press that button and the survey will open in your web browser. It's a very short survey. It should take you literally not more than about 30 seconds of your time. You will also have the ability at the end of the survey to request a free limited time trial license for testing the site compliance module. I hope you have enjoyed the webinar today. Please look forward to some more information from us in the early part of next week, including the link to this the video of this presentation. So have a good day, evening, or night, depending on where you might be in the world, and thanks for your time and attention.